Up. Yes, now we're recording. Welcome everyone. I think more people are likely to join in as this is a separate event from the other NGI Forum events. Like, it's not hosted on that website, so people will end up here. I expect some people to find us in a minute or two, but we can kick off anyhow. Welcome to everyone, and thanks for everyone joining already. My name is Joost Achterhoek. I am with the NLnet Foundation that's spearheading the NGI Zero grant program. This is a workshop that we're hosting on the topic of open hardware and the efforts that the Next Generation Internet program is supporting in open hardware, where we first present a number of NGI Zero projects working on open hardware components, tools, infrastructure, after which Rob Taylor of LibreCores and ChipFlow will have an industry panel which will take this topic of the possibilities of open hardware for a future EU semiconductor ecosystem landscape. So first off, I have a few slides that I'll go through rather quickly to give time to the actual presenters, but just to give everyone some insights. As I mentioned, we are part, NLnet, the NLnet Foundation is part of the Next Generation Internet Research and Development Program, which is an effort by the European Commission. And we, as a foundation, are hosting two research and innovation actions. And you can find those two green ones at the top, one focusing on improving search and discovery, and the other one on supporting development of privacy and trust enhancing technologies. Let's see, some key characteristics of how we approach funding. We have a strict requirement for projects to deliver on free and open source software, open hardware, open standards, open research, and we host a bi-monthly open call every 2 months for projects between 5 and 50,000. So a very lightweight manner to support innovative research and development. Both calls having the span of 5.6 million euros that we've been granting between 2018 and 2021. Actually, November this year is where the entire program will wrap up. And we're proud to have currently over 280, if I'm correct, projects funded, which is awesome, of course. You could see in the slide before that we aim to not just talk the talk, but also walk the walk, meaning that we think it's worth more to actually support projects than then just throw money over the fence. So we try to, and for projects and technology to be scale to internet level, a lot of critical dimensions need to be addressed that projects on their own and developers or businesses on their own would not be able to do. So we have a host of internet expert organizations joining in the NGI Zero consortium. It's a collaborative effort where we address issues you can see here like security, accessibility, licensing, standardization, also packaging with the innovative NIX package manager. And a number of other dimensions that we'll not go into too far. All of this stems from the NLnet Foundation, which is what I'm working with. And that is a foundation that goes back to the early internetworking days in the Netherlands, in Europe actually, very pioneering work. For example, the first open internet connection between the US and the EU. And since the early 80s, this has been a foundation funding open source software, open standards, and open hardware to contribute to an open information society. This is just a snapshot of projects that we have been and are currently funding, a number of which will be presenting later and will be joining us, hopefully, of open hardware components. I might call it chips here for the sake of brevity, tools and infrastructure. These slides and the links all, of course, will be released afterwards, so you can look all these awesome projects up. And for that leaves my end of the introducing everyone and trying to paint the stage for everyone to start their own talks on their projects, which is what we always like to put first. So first off, I'd like to invite Thomas Kramer to take the stage. I will make you presenter in a minute and present his work on LibrEDA. Minutes. Thomas, I am able to see you but not make you presenter for some reason. I've made you moderator. You could try to take the presenter role.
Well, let me find out how I can do that.
Maybe 1 minute if I take presenter role and then would hand it off to you.
Now I can do it. Now I can take presenter. Shall I do that?
Okay, yes, very good. I'll turn off
Good.
my...
And then I guess I should be able to share my screen somehow.
Yes, there's a button on the lower right-hand side for you to share your screen and to give a presentation. Also to share your webcam, which I will turn off right now.
Good here. Oh, I found it. So I believe you should already see something, do you?
Yes, that works.
Good. And do you see slides?
Yes, we do.
Good. So, well, thanks for the introduction. And I will now quickly talk about the project that is founded by NLnet and the NGI Zero, which I'm working on under the title LibrEDA. And it's about Libre electronic design automation, especially for ASIC design. I'm also a member of the Free Silicon Foundation. This is why I also put some advertisement here. So just when we talk about open hardware, I noticed that sometimes there's some confusion. Well, there's many types of open hardware. I think for most of you will be clear, but I thought maybe it's good to give a short overview. So a 3D printed pen holder standing on my desk could be open hardware, but that's not really what I'm talking about today. Then there's Arduinos, Raspberry Pis, very cool projects that are open hardware to the extent that the PCB is open, software is open, but the silicon chip mostly is closed. Then there's things like the Lattice ICE40 FPGA, which is opened thanks to reverse engineering, so that it's openly documented. Still, the silicon chip is closed. Then there's things like RISC-V, which is an open instruction set, but it's only an instruction set, so the actual silicon implementation might still be closed. Then there were some efforts in the last few years to create open source silicon chips like the Raven chip or Open Titan. In this case, it's the RTL, so the high-level description is open source, but not the layout. Then something that probably most of you heard about is Skywater, the silicon fab that opened their process together with Google. So there is a open PDK process design kit available, but still it's a closed process, and this did not happen in the EU, and I think this workshop is about silicon in the EU. Then there's efforts that you'll probably hear about today again, for instance, LibreSilicon, which design an open process and an open PDK. So I will talk about the silicon and especially also about tools to actually design the silicon. So when I talk about open hardware, I mean free and open source tools, CAD tools, for making the designs of silicon chips. I also talk about the sharing of hardware designs and the knowledge behind. I talk about open standards and, of course, the freedom of the user in the context of silicon chips. So, which means the user should be able to study a chip, use it for whatever he wants, share designs, and also improve upon designs. So my motivation basically is that I realize our society depends highly on silicon, but still silicon chips are black boxes, and this comes with a lot of security implications. Then control over silicon is centralized. There's also centralized control over major EDA tools that are basically managed by monopolies, which give them under very restrictive licenses. So in practice, it's quite hard to openly share designs, and of course it's hard to study designs, learn up from them, and improve them. So as an example, regarding myself, I was working in a group that was designing integrated photonics for high-speed chip-to-chip links. And there we noticed that modifying and extending a closed source tool is a pain, but actually important for such innovation. And also we noticed that export regulations can be a killer, especially if you fabricate something in the US and want to ship it to the EU, and it falls under export regulation because it contains photonic technology. So another reason why I think FOSS is a great thing, I'd like to use free and open source tools for teaching, also in research, and I'm convinced that it can speed up innovation. So now to my actual projects where I'm working on. As you've seen before, is LibrEDA, which is an ASIC place and route framework. So to actually place standard cells and make the connections based on a synthesized netlist. Then there's another side project which I started earlier, and currently I'm actually mostly working on that to get some things done, is LibreCell, which is a standard cell generator and also a characterization tool. And its intention is to create standard cell libraries. The standard cells, you can see that here down on the right. They're basically the building blocks of digital circuits. And then LibrEDA can be used to assemble these small blocks to a bigger circuit. So LibrEDA is not an actual place and route tool. It is more a collection of libraries that you can use to create a design flow. So this is why I'm calling it a framework, and it's written in Rust. And the idea is that the development of place and route tools should be simplified with such a modular and reusable framework. So therefore, the framework aims to provide fundamental data structures, for instance, for layouts and netlists. It provides interface definitions for algorithms like placement and localization and routing. And it provides libraries for input and output of common formats, such as Oasis for the layout, Verilog for netlists, LeftDef for libraries and designs. And it also comes with example implementations. So since I'm only a single person working on that, I can provide some examples that will not be performant. They might not scale to big designs, but at least I can show how the framework can be used. So there's a lot of work in progress. Probably the most critical thing right now is the signal router where I'm working on, and I think it's probably also one of the more challenging tasks. Then there's some outstanding things like power router, clock tree generator, rebuffering, macro placement, then extraction of parasitic capacitances and resistances, or at least some estimation of the wire delay, and integration of timing analysis. And of course, there's many more things that could be done. And next to it, also realized it's actually nice, especially for teaching, to have some very simple place and route framework that just illustrates the concepts and algorithms. And therefore, I also started working on a Python plugin for K-layout that kind of redoes this framework of LibrEDA, but just in very simple Python code. And it's really intended just for teaching and like also self-education. And also for me as a playground to try out things. So then, second project, LibreCell. So what it's basically about, it takes a netlist of a standard cell. So this is a transistor-based netlist. And then there's a tool, LC Layout, that takes this netlist and transforms it into a layout. Of course, there's some inputs like design rules and sizing of all those parts. Then the second tool, LC Time, does SPICE simulations of the cell and figures out the timing behavior, like the propagation delays through the cell, or setup and hold constraints, and also figures out how much power the cell uses. So, for instance, characterization can actually be split into two parts. One is also cell recognition, and this is also something that I'm currently working on. And cell recognition is about some sort of reverse engineering. So you look at the netlist of a standard cell and find out what is it actually doing. So is it an XOR gate? Is it an AND gate? Is it a flip-flop? And based on that, you can then decide on how you have to characterize it, how you have to run the simulations. And then you can do characterizations. So here on this plot is a simple example of inputs and outputs of an XOR gate. And then based on the simulations, you can actually measure the delay from input to output. Good. That was it already from my side.
Thank you very much, Thomas. Thanks for this brief but yet insightful introduction to everything. Also nice to see that Droste effect always. The next presentation was planned to be from Staf Verhaegen from Chips for Makers. He's having some issues with joining the call, so for the sake of time, I would suggest we then move on to Luke, Kenneth, Casson, Leighton's presentation, which he provided to me. It's a pre-recorded presentation. The pre-recorded presentations that I show to you all would not be shown in the recording. So for posterity's sake, should you want to view this presentation, it's very interesting. Please follow the link that you can see on the screen right now and that you can find in the slides, which of course we will make public and show afterwards. So 1 minute as I give the floor to the virtual Luke. Thank you very much, Luke, for sharing that pre-recorded presentation. I'm also happy to see you are seeing Staf Verhaegen was able to join us.
No problem. Thank you.
Hi. Yes, for anyone who was joining in, or for anyone viewing this after the event is over, there was a pre-recorded presentation that, if I'm correct, you would not be able to see. In the slides, you can find the link to that presentation, so you would be able to check back. I will now leave the floor to Staf Verhaegen, which I will make presenter in 1 minute. And as you can see, he is the lead developer of Chips for Makers ASICs, and he should now be able to give us an update on the work that he's been doing, amongst others, funded by the NGI Zero program. Take it away, Staf.
All right. Do you see my slides?
Yes, your audio is a bit low. That might be me, but you are audible.
Okay. So I will try to speak out. It was already stressful still now, so it's good to get away of the hormones. So I want to talk about Chips for Makers and how I came up into the NGI Zero project, and also a little thought on how it can fit into the whole European semiconductor industry. So first, I will give a little bit of my background, because that's nice, because it will lead to the rest of the presentation. Then what is Chip for Makers and why am I doing this? And then talk about Chip for Makers and NGI Zero and libre-SOC, and then about Chip for Makers and the broader semiconductor industry. So who am I? So I'm employed. I was employed from 95 to 19 at IMEC, which most of you probably know. It's the biggest research institute for semiconductors, and it's located here in Belgium. And the last part of my work there, I was working on the so-called DARE library and design framework, which is design against radiation effects. So it's a radiation hardened design. So what I did there is development of radiation hardened cell libraries and IO libraries and an SRAM compiler. These are components that they use for making designing chips. So I also then set up and maintained the internal flow that we used for designing. So I had to support all the designers, also the analog designers. So I know a little bit about analog design also. And I also did customer support for the DARE libraries. So in that respect, I learned to know the full flow from RTL to GDS because I had to triage the issues that are coming in from customers and then know who to approach to answer the problems, and also hopefully already could help them without needing to go further. So that development was done in the IC Link department of IMEC, and this is also known for EuroPractice, which is providing ASIC services for academics and for SMEs. They also have an MPW ASIC service, so I was in close collaboration with them also. So I was knowing and how this system works, and I had insight in how it worked. But next to my professional career, I am also a retro geek. So I like both Commodore 64, Amiga, and it's not only nostalgic. I'm still from time to time doing things on that. And also I'm an open source developer. So I'll be working on an open source implementation of Amiga OS. I'm using Linux, Python, and all these things. So all these things combined, I had an idea. I wanted to make a retro-inspired system on a chip. And I asked my contacts at IMEC for a quote. And then this chip was not so demanding, so it could be done in a mature technology node. So for example, 0.35 micrometer. And then the quote was that the processing, the making of the chip itself would cost less than $5,000. But going from design to silicon, so the tooling, the EDA tools, would cost more than 30,000 euros. And then I realized that we should bring the EDA tool flow cost more into line with the cost of mature chip production. And that's why I talked about open source EDA flows and these things. So, and then if you have the open source flows, what I want to achieve is, as already Luke mentioned in his presentation, is to cost ASIC service, so that people can make chips for 50 chips for 750 euros. I think that'd be good for funding of maker projects, not necessarily targeting higher volumes. So, but I want to make it fit for makers, hobbyists. So it means signing no paperwork, so no NDAs or other licenses to be signed, and open source tooling, so that people could also add to the tooling things they wanted to see implemented, and you're not on the mercy of a commercial company to do what you want to do. So then the next question is, how came I into the NGI Zero and the LibreSOC project? We had some common interest between me and the LibreSOC project. So the LibreSOC project was looking for a cost-effective prototype possibility using libre-licensed software. And of course, I could use a good use case for what I was doing. So then me, and together with the Lib6 department at Sorbonne University, are then developing a flow to allow to make a 0.18 prototype for LibreSOC. And Luke has already talked about that in his presentation. So And then my last slide is that how do I see chips for makers in the broader European semiconductor industry? I agree that low volume, low cost ASICs alone will not be able to drive a European semiconductor industry, but it can help growing the ecosystem. If you increase the pool of people who do have ASIC design experience by making their own chips, you will also increase the demand for high volume ASICs. Having such low cost options will also make it possible not only for academia or for professional design houses, but also for makers to make their own chip. And when you have a lot of people doing things, you will also drive innovation of the toolchain by a lot of people doing it the open source way, scratching their own itch, and then also being able to be used by other people. So, like for example, in the Linux ecosystem, where you still have people maintaining a Motorola 68000 Linux version next to the 64-bit or the RISC-V Linux. Okay, that was in short what I wanted to say about chip for makers and connection with NGI Zero.
Thank you, Staf. It was a very clear introduction to what you're doing and how that fits within the broader context of, well, the topic of the future of the European semiconductor industry. Thank you very much for that. I think now we would like to move on with David Lanzendoerfer.
You've got muted.
Am I unmuted now? Okay, that probably was a quick slip. David, you provided your slides, if I remember correctly, earlier on. So if I make you presenter, you should be able to just click on them, if I'm correct. David?
Yes. Do you hear me?
Yes, we can hear you.
Okay, now you see my questionable face.
Yes.
And there we go. Right. Okay.
Great. Awesome.
So let's see whether it loads.
Yes.
Here. Okay. Hello. As I was introduced, my name is David. I'm the founder of the LibreSilicon project. The aim of it is to be a free and open source semiconductor manufacturing standard. That means our aim is to standardize a certain flow. Hey, hi, Christoph. A certain flow node of how to say semiconductor geometry. One cool thing is there are no NDAs because it's under a free license, and it's supposed to be usable in a garage environment as well as in an industrial environment. So the aim is to be so robust that it produces working transistors no matter whether you use a homemade tools or whether you use professional tools. And so the idea is to have basically portable design resulting out of that, where you can make a prototype in a basement and then someone can reproduce the same circuit in a mass manufacturing environment, etc. The project includes also FOSS tools, like a standard cell generator from Thomas. He already went into there. As I said, that's basically Thomas. Is these LibrEDA. That's basically this standard cell lib generator, synthesis, place and route, and so on. Features. So the basic features: transistors, MOSFETs, field effect transistors. Then you can add, if you have the additional tools required, you can do B junction transistors, diodes, diverse types of capacitors and resistors, Sonos flash, flat cells, and complex IP core, everything you want, because it's super robust, flexible, because of its free and open source nature. We did that because NDAs are really a showstopper when you want to start developing semiconductors. Factories with their NDAs and the proprietary IP cores, they vendor lock-in. You're limited to specific time slots when you want to do an MPW. And then, of course, because it's proprietary, you have potential hardware backdoors. You have no chance to really spot on the fly because you don't really know how the circuitry is supposed to look in detail. That also prevents you from having audit. And they sell you JTAG. They basically drill open security measures you put in place with your ASIC by adding these testing features, JTAG and other hardware, essentially hardware backdoors potentially. There are a lot of things you don't really have control of it. They tape out actually at the end. So I started 2017. I started developing a process flow. Back then targeted at the semiconductor lab in Hong Kong. That's the HKUST, NFF, Nano Fabrication Facility, Hong Kong University for Science and Technology in Clearwater Bay. 2018, we made our first test wafers. Here you can see switching of a transistor. Here some logic cells and me in a bunny suit. And yet now recently, that was already mentioned, we used our cell to generate standard cells for the Skywater factory and for the 180 nanometer process. And we hope that we can convince some European factories to also give us their design rules without NDA so that we can generate standard cells for their process and share them online and verify it and provide Libre standard cell libraries for their proprietary process. That's so we have multiple things. For instance, closed loop glove boxes. That's basically a micro clean room where you go in with hands, with gloves. A patterning system. We going to use DMT, the micro mirror displays, and visible UV LED. This way we can make inexpensive patterning like Sam Seeluft did. Then we need, as I said, so CVD and RTP. There I have to search a little bit for a little bit more reliable materials so that I actually get a low pressure chamber and not a pipe bomb in my garage. And everything, because it's the space constraint, it's a garage, I go for the smallest available size of wafers, 2-inch. So that you get an idea, here is implementation like Sam Seeluft did. It's basically it's a reverse microscope. Essentially, it's a microscope table with fine positioning. And our approach is to use modify basically the RipRap software, the G-code interpreter on an Arduino with Pololo stepper, drivers, and so on, and use positioners and modify the RipRap software and hardware to a degree that it becomes a and in a way that it's actually not tinkered together widely with scrap parts, but with parts from catalogs that you can manufacture more of it and actually sell that to other hobbyists who are looking for such a stepper aligner as well. as soon as that works, the idea is to first we start with 50 microns. As soon as that works, we scale down to 1 micron, and as soon as everything works, we can switch the inexpensive DMD chip for visible UV light with alternative from Texas Instruments, which is made for hard UV light specifically, and survives that. And then we can reduce the feature size, and actually at some point might actually reach a point where we have to use immersion technology in order to fight the diffraction issue when you go sub-micron.
David, would you be able to wrap up with the next slide? I think it's a very interesting presentation.
Yeah, yes. And quickly, I have like just a few. So that's just that you get an idea of the glove boxes. That's not really world changing. It's just a glove box with filtration, EPA filter. And yes, that's basically it. We have to improvise the tools for the garage setup and get some clean room environment in the limited space I have down there. And later on, we would like to scale that up and actually provide prototyping services for people who don't have garage space or the money to get their own equipment. But yeah, that's where we stand. Thanks.
Thank you very much, David. I'm already seeing a lot of excited people in the chat that are very interested to get their hands on your tooling. I think it's a wonderful way that you're demonstrating this hands-on, like as Michiel mentioned in an earlier presentation, permission-free, permissionless innovation, which this would be able to actually kickstart, which is awesome. So thank you for that. For the sake of time, I'm speeding a bit, of course, through everyone, but I would still like to leave some room for that for the panel. So right now, I would like to give the floor to Zhangjun Zhao, hi, of the Open Wi-Fi project. Let's see if I would still need to make you presenter. Yes, I would. Okay. You're now able to either share your slides or share the screen, which is the bottom right side. That's usually easiest. And I'll turn off my mic and my video so you can take the floor.
Yeah. Can you see my slides?
Yes.
Okay,
yeah,
good.
The audio is a bit low, but it's understandable. But... Okay,
I will try it louder.
Yes.
Hello, everyone. Let me start the timer. Hello, everyone. This is Xianjun from IMEC as well, I would say. Yeah, I'm currently still working in IMEC in Belgium. I work in the ID lab inside IMEC. The location is in Ghent in Belgium. So I will introduce what is Open Wi-Fi, what are the progress now, and what is the plan, and finally some open questions. So what is Open Wi-Fi? Well, I guess some of you might heard about Open Wi-Fi recent days, but we are not that Open Wi-Fi, the global open access Wi-Fi system. Yeah, we are the free and open Wi-Fi chip design. Fortunately or unfortunately, the name are collide with each other. But here, Open Wi-Fi is an open source or free Wi-Fi chip design. But currently, it's not a real chip yet. It's still run on the FPGA platform, together with some off-the-shelf analog R frontend to do the verification. And it's also used a lot in our internal research activity. And meanwhile, we also release it in a free and open source world under the 8GPL v3 license on GitHub. You can just search Open Wi-Fi, you will find our GitHub. I think our item is on the top in the Google. Here in this page, you can see we already got lots of users on GitHub according to our observation. If some people come to us to ask a question or to discuss some features, we know they are actually using Open Wi-Fi. Most of them, I think, are from universities, research institutes in the US, Europe, Asia as well, and also Australia, I think. Also some industrial companies, but they are in well, you know, the traditional companies in the traditional business model. On GitHub, our software plus hardware repository already achieves lots of results. I would say around 2K stars and around 300 forks and many watches. The software here means the Linux driver and our user space control tool, a small tool for people to access the driver and the FPGA. Hardware means the FPGA design. Most of our design are written in Verilog. I believe Verilog is still the most popular chip front-end development language now. Maybe in the future it could be Chisel or Spino HDL, but now I think it's still the Verilog is the most popular one. Now, if you check the topic, Verilog topic on GitHub, our project is at the rank 2 or rank 3. Well, if you are interested in using openwifi instead of customize it, develop it, actually it's quite simple. You just download our Linux image from GitHub and buy an off-the-shelf FPGA board, right? It's not from us, it's the commercial FPGA board. And you flash the image to the SD card, insert SD card to the board. Meanwhile, connect your board to your home broadband router and then to the internet, right? Then power on. You can see the SSID openwifi and you can connect it to surf on the internet as the real Wi-Fi router. But you do need to check your local macro power ISM band regulations. I believe the current SDR platform we support, the transmitting power is well below 1 milliwatt, but you need to check your local regulations if you really want to use it in the open air. A different country or different region, they have different regulations, I think. But I think in most of the locations, most of the countries, well below 1 milliwatt in ISM band should be okay, but do check your local regulation. Progress. In this slides, as you can see, the project born outdated because when the project was born at the end of 2019, actually before that, we already have 2 or 3 years internal development in European research activity, ORCA. But at the end of 2019, we decided to release it in open source. At that time, we support only 11 AG, born outdated, right? Because as you know, AG was there 20 years ago. Then we try to catching up the state of art. The 11N is the first step under the funding from NLnet. Now we support 11N now, which is also known as Wi-Fi 4. And now we are working on the packet aggregation feature on the 11N. The packet aggregation is a key essential feature for the Wi-Fi system. It's imported in the 11N, and then after 11N, the aggregation is a mandatory feature. By default, it's on for the AC and AX. And now we are working on the AX, which is also known Wi-Fi 6. By the end of this year, we hope we can release the basic Wi-Fi 6.5 physical layer implementation. And we also are working on the MIMO feature. When it gets stable and mature, we will release it. And now the project, beyond the standard stuff, we are also becoming unique compared with the COS Wi-Fi chip. For instance, we have dedicated on chip Wi-Fi CPU connection, right? In the same FPGA SoC. We have real-time and low latency. And we also support the CSI sensing and anti-CSI sensing. It's CSI fuzzer. We can prevent the unauthorized CSI sensing. And we as SDR platform, we support IQ sample, but not like other SDR platform. They always stream all the IQ to your computer continuously. In Open Wi-Fi, you can do the IQ sample capture by trigger, because in the Wi-Fi chip, there are lots of trigger conditions you can define event inside the protocol. And fuzzing, you have full access to the low-level, deep-level stuff. You can do a low-level, deep-level fuzzing. And your idea, your applications matter. If you can come up with new feature, new idea, very unique, very special things, I think that would make the Open Wi-Fi more special. And I think that's also very important. Okay, finally, some open questions. From open source project, actually from our current FPGA design to a real chip, I would say not just click the button, but according to the previous several presentations from the chip form makers, from the LibreSilicon, I feel that, well, something exciting is happening there. But again, EDA software design process, design flow involved heavily, not just click the button. We need people, we need resource and funding. And another very important question is about sustainability. Actually, I mean the commercial success. I think that's also a very important aspect of the open source project or the liberal free project, because the commercial success could spread the good things all over the world, right? Much widely, much broadly than just volunteer-based or funding-based. So can Open Wi-Fi chip be a successful business? Because if we analyze the current Wi-Fi chip market, it's purely game of the volume, right? Then to achieve a certain the volume, can we identify a new area like a blue sea, or we jump in the already the red sea with those big Wi-Fi chip makers? Where should we go, and in which case can we win the game of the volume? Yeah, that's my presentations.
Thank you very much, Hyunjin, for this insightful presentation. I think the open questions that you've been raising are very interesting. Maybe some things we could also consider for the discussion afterwards. For the sake of time, we are a bit cutting it close, of course, always with these online events, with events in general. I would like to now give the floor to Charles Papon, if I'm pronouncing that correctly, who, if I saw earlier, was able to join us, and who I will make presenter right now. Let's see. Okay. Charles, you should be able to share your screen or share your slides with the button below. But I think your screen, yes, and that works.
Oh, good. Okay. So yeah, who I am. So Charles Papon. I'm a hardware software. I have a software and hardware background. I'm the main dev between the three projects I will present you now. And so basically, first I have to explain you on which platform I'm working on. So if you have some hardware and you want to deploy it, you can either design the ASIC and make the production of the ASIC to deploy your design on it. Either you can use an FPGA. And basically FPGA, just to explain really what it is many gates on a chip, but the interconnections between those gates can be reconfigured. So that way you can develop your hardware, your design, and deploy it on the FPGA. You don't have to create a new silicon for that. You can just pick an off-the-shelf FPGA and upload your design on it. A bit like you deploy software on a PC, you can deploy a hardware design on an FPGA. And that's really the platform I'm working on. And basically, from an open source perspective, this kind of platform has quite a few key advantages. Basically, it has a really low initial cost. That means people, users, academics can really easily afford it. You can find quite good development kit for $100. And also, the time that you need to iterate your design can be really low. It can be as low as a few minutes. Not saying it is a good practice, but it is a really interactive process. So now, okay, the project I'm working on, the first one is PanelXDL. So basically, when you want to design your hardware, your digital design, long time ago, maybe people were still drawing logical gates and connecting them together. Then they moved on using code to describe the behavior that they want in the chip. And the industry standards for that are VxDL, Verilog, and System Verilog. The issue, for instance, with those languages is that they have a lot of legacy behind them, and they are always evolving in a very incremental manner, which means there is never a big paradigm shift. And as a hardware world is way more conservative than the software world. So basically what PanelXDL try to do is to bring new paradigm on the table, like using software approaches to do the elaboration of the hardware that you need by using object-oriented programming, functional programming, and many other design patterns taken from the software world but applied to the hardware elaboration. And so PanelXDL is not the only open source attempt to bring this kind of new things on the table. There is like NMigan, there is Scheisel, and there is many others. And also what does that project bring is standard library with a few key components if you want to design your chip, like DDR3 controller, Ethernet controller, USB host controller. And on the top of that, for instance, there is another project, or everything, all of this is free and open source. It is VexRISC-V. It is a 32-bit CPU optimized to fit well on FPGA. And it supports multi-core, memory currency, can run upstream Linux. Recently, we added 64-bit FPU and IES. And so what it allows people, the fact that you can get an open source CPU based on a more or less open source instruction set, RISC-V, is that people can analyze it, can take a look how it really works. They can extend it, they can add custom instructions. For instance, some people were adding some crypto acceleration in VexRISC-V because it is based on PanelXDL, which really allow to design things in an extensible way. Like there is a plugin system, you can add custom instruction in a really smooth way, for instance. So, and then on the top of this, there is Saxon SoC, which is another project based on the two previous one, where the goal is to take all those components and integrate them into a SoC. So, for instance, here you can see a dev kit, a FPGA dev kit. It's not an expensive one. It's about $130. And on this dev kit were integrated like two RISC-V CPU, two VexRISC-V CPU with a shared FPU, with a DDR3 memory controller, SD card, Ethernet connections, USB host port added recently, so you can plug your keyboard, mouse, USB stick, USB hub, all this kind of connectics on it, video output, audio output. So basically, with this framework, for instance, there is other frameworks, just to give an example. You can really build the SoC that you want and deploy it on an affordable FPGA kit and extend it the way you want. And the state now is that, for instance, on this dev board I've shown you before, you can have Linux running with build root as an operating system. And here's a screenshot of it running X11 with a few applications, like, for instance, MPG-123 to decode MP3 file in live and play it on some USB helmet, some web browser like Dilo. They're quite limited, but still, it's really a proof that the system is stable and working. You can run quite a few software packages on it, and basically having all this ecosystem, which is open source, really allow to keep some freedom to analyze how it works. And also, I forgot to tell that before, but for instance, in the FPGA world, the FPGA vendors have quite a bad habit to try to lock you down to their tools. Basically, what they do is they offer some more or less free tools for you, but basically, as soon as you start to use it, and that's what the industry is really doing when they do FPGAs, they really use the vendor tools. they end up being really locked down, because as soon as you use the tool, you can't migrate your design on another FPGA vendor. And really by having this whole open source approaches, really avoid that. And people have really made crazy experiments with it, as I said before, adding custom instructions, custom functionalities. So yeah, that's the project I'm working on. That's it.
Thank you very much, Charles. That was a very concise but informative presentation. You're really good with time restraints, which I'm usually horrible with. So that's awesome, because that still gives us quite some time for the discussion. I think there are a lot of components that we've talked about so far that would be interesting for the discussion, but there's also an awesome topic for the discussion already present here. 1 minute, I will take presenter so you will switch back to my slides. Yes, because for the sake of this panel discussion, in which we talk about the role of open hardware in the future EU chip ecosystem landscape, so to say, we've invited expert Rob Taylor, possibly familiar to you, or familiar to you all mostly, from the Libre course project, and his, if I'm correct, quite recent efforts with ChipFlow, on which he will be able to explain a bit further. Rob, feel free to take the floor and get the discussion started. And thanks from my end for everyone joining in on this discussion from various dimensions. We've been hard at work pulling all these interesting voices in here. So, Rob, take it away.
Thank you very much, Joost. And thank you for such an interesting set of presentations we had. And I was blown away by at least a couple of those. The thought of people making chips in their garage, I mean, that's that could be a whole new way for the industry to go forward, right? To take that RepRap model and go on. So I'd like to invite the rest of the panel members to come up and switch on the microphones and video cameras. So that's we're going to have for us today. We're going to have Bunny Huang, who's you'll definitely know from his work with Be Trusted and Novena. Olaf Kindgren, who has been plowing the field of open source silicon for well over a decade now, and is definitely one of the characters of the scene and a real cornerstone of the ecosystem. I'd like to welcome Sally Ward-Foxton, who is the European correspondent for EE Times and the resident AI expert. We're really lucky to have here today David Prescott, who's the technical director of a fabulous design house in the UK here called NSilica, who regularly helping real customers get real chips out into real products. We've got Maria Envelado, who is the R&D project leader for the Nano and Digital Technologies Hub at IMEC. So she's looking at ways to where the future is for IMEC and in terms of providing these services and enabling new classes of customers. We've got Jana Nida, who is the coordinator of the Advanced Materials and Computation Cluster at INL. I'm really interested to see learn about her thoughts on how some of this could apply to novel new techniques and materials. And we have finally Mohammed Kassim, who is the co-founder and CTO of the platform of eFabless, which is the company that's behind the Skywater 130 process, which is currently the only way you can build a chip completely open source all the way down to the PDK and the GDS that goes to the foundry. So welcome everybody. Thank you for joining. We're kicking off today really looking back at those presentations, and I'd like to just open the floor. does anyone like to share what their thoughts were on the projects that we've seen today, and have there been any large surprises for you, any of you? Now, if I don't get a volunteer, I'll name some names. Maria, do you have any thoughts?
Okay. Can you hear me well?
Very well, thank you.
Okay. I saw a very high level of sophistication in these projects. I was not that familiar with the open source hardware community until recently. And well, also, especially David's garage approach, it was very interesting. It's really innovative and I really liked it. So yeah, I'm very happy to see that people is also tackling different problems or from different sides, and they are trying to develop an ecosystem. So I think this is very important and it's very cool. So congratulations, all of you.
Thank you, Maria. Anyone else like to throw in, follow on from what Maria was saying?
Well, from my perspective, there was not a specific large surprise, except that just my observation when I see the work is the amount of community work across the board on the EDA side, on the hardware side, that is actually addressing the different pieces, like even communications, like the Open Wi-Fi project. You know, without communications and secure communications, a lot of that stuff wouldn't work. So I am actually excited to see the several tracks of EDA and development in that direction in different ways, which is good for the entire open source chip movement. The second part is that I cannot wait to start. I was talking to Bunny and just saw also the Open Wi-Fi project, to have other community members work along these projects and actually start creating some ASIC pieces of these projects, and over time move along to something that is completely open all the way to GDS. So yes, so it's actually very exciting, and I'm very happy coming from a semiconductor world for all my career. This is the most exciting period in that industry right now for me.
I think it's interesting to hear about some of the new concepts and ideas, though, isn't it? The spinal HDL, it's really addressing the lack of progress in design abstraction. We've heard about RTL, but RTL is, that appeared in the late 80s. That transition from schematics to RTL, things have really stalled. I'm more skeptical of some of the approaches, but I think there needs to be change. It's interesting to hear some of the ideas.
Certainly one of the things that I've kind of observe in this space is that the old economics of it has kind of meant that a lot of novel technologies and approaches kind of get killed off quite early, right? Either the team gets bought into one of the big EDA vendors, or into one of the chip the fabless or fabbed semiconductor manufacturers, and that innovation kind of gets lost. And I'm very enthused about what we can do by increasing that rate of innovation by enabling these open technologies. And I think, definitely, I agree with David. Some of these things are kind of a bit, maybe they're not going to work out, but some things are definitely going to work out, I think, and be really relevant.
Well, just a last comment on this. I think that's the nature of innovation. People are going to try using the resources available. Many tracks are going to be in parallel. Some of them are going to get more traction than others. The one thing that I do believe in wholeheartedly, that's why our company exists, and hopefully other companies like this exist, is the commercial aspect of the application of all this progress into commercial solutions, like hardware solutions. How do we make more people using hardware that is developed using these types of, IP or software, and that is the way that's going to sustain the progress and propel the progress. It's not the money; it's the usefulness to the world using products.
See a lot of nodding faces. Jana, would you like to follow on?
Yes, so this one of the words that was mentioned a lot of times was like teaching and education, and I think it seems to me, so as I'm not from the open source area but from the research area, of course, our researchers also most often, when you have tools that are easier accessible, it's the thing that you play with and that you use for exploring new things. So in the end, when going on and to go a project where there might be more funding, still you have learned with open source tools and to be bringing this to the new projects, right? So if there was more of these projects available also on open hardware, certainly, in more, I think it may have an impact later on to be actually picked up, simply because, the younger generation would be trained in these tools and using these tools. So what I found interesting was that many of the projects presented were so connected. So the LibreEDA is used by others. The chip for makers is happy to have a use case from the LibreEDA. So that I found quite interesting. So it seems, so I'm not from the community, and curious to hear the feedback. It seems to be like the community knows each other very well and knows the project very well, and is following the progresses from each other, which seems to be a very healthy community. And so in general, I think I was quite impressed by that.
Thank you, Jana. Thank you. Bernie, Sally, we haven't heard from you. Sally, do you want to go?
Yeah, so all the presentations I found were very, very interesting. From my perspective, I'm used to seeing the concept of open source hardware applied to RISC-V and core development, that kind of thing. So it was really interesting for me to see some of the efforts going on in open source EDA tools and with open source manufacturing as well. I mean, I cannot believe really that David there with his presentation where he's building a fab in his garage. I was astounded by that, quite frankly. I think he said in the chat box following his presentation that he plans to eventually make a prototyping service, or even possibly even make his own foundry one day. I'm interested to hear what the business model is going to be for this foundry that he's going to make. But I thought he's doing incredible work for sure.
Rep for ASICs, right? We know how that much changed the manufacturing world. So yeah, funny. I mean, you know all this already, right?
Well, I mean, I think the problem was I didn't read my homework, but I didn't realize I was supposed to dial in earlier and watch all the presentations. I actually dialed in like 15 minutes before the call time, and I actually had another call beforehand, so I only saw I saw Charles's presentation and the tail end of the Wi-Fi, but they're both very interesting projects. We're a direct user actually in the precursor Be Trusted project of the Vectrus core that he's working on, and it's been like incredibly useful to have it. And as a sort of like, I've been sort of working on open hardware back when people kind of laughed at the whole concept and thought it was a stupid thing. And it's been very I don't know, cathartic almost to sort of see real communities come together, creating things that like are not just usable, but actually capable of displacing incumbencies at this point in time. There's a real sort of, meat, a real substance to the movement at this point in time.
I think you're right. It feels very much like there is an uptick, at the knee of an exponential curve happening in this space. And for me, I'm an old open source hand. It reminds me a lot of like the late 90s, early 2000s. In open source software, And we kind of know where that went, right? Now I think you can't. No one could even consider making a new software product without using open source, right? And almost every product in the world you interact with today probably has open source in it at some point. So that kind of leads me really nicely on to the next question I'd like to throw out there to the panel, which is, do we think that open source can have as much an effect on the silicon and semiconductor and VLSI and future paths, Jana? Can open source have as much effect on that world as it's had on the software world in the last 2 decades? I'm sure kind of Olaf, Buddy, Mohammed going to throw some ideas in, but to open the floor.
Well, you made the analogy with open source software in the late 90s. I would like to make another analogy, and that is with the minis and microcomputers in the early 80s, where we had these people running mini computers who knew how computer worked, and then we had a lot of people buying these microcomputers who didn't know how to properly use a computer, and the big guys were laughing at them. And this is where the innovation happened, because it was available. Unless some of the other panelists has mentioned before, just making things available will bring innovation. You can start small, you can try out your ID, which is not really possible today. I mean, for my own projects, if I would like to get an estimate of how this would perform on an ASIC, I would not be able to do that until very recently with the OpenLane project.
Yeah, absolutely. That's a really good analogy.
So, just a comment here. So as I mentioned, my background is 100% in the chip development, including smartphone applications processors. Now, here's my view. Given all that, I think the shackles around the open source chip design are artificial and economic. They're not technical, for sure. So, and that is if it was technical, it would have been much harder to achieve. Okay, even if it's technical now, it's attached to capital. But and I mentioned that I used to work, for example, on 130 nanometer, basically almost 20 years ago. And yet today, that's an example 130, but obviously there are many applications that could use that. Even the actual process development and progress is driven by economics, not just because they want to have a smaller transistor. It's economics. I want to have more chips per wafer, so I can have volume, so I can stuff it with more and obviously get some improvement in power. But that was the goal, to drive the technology. If you look at the advances in technology, process technology, the way it's working, there was no time. It's almost like every 2 years you jump a node from process to process. There was no time to actually live on one node and optimize architectures. Mm-hmm. And there's a lot of room to actually use earlier process technologies. Call it, even 28, 65, 130. I will jump back to optimize architectures and actually get there and develop real useful competitive and chips. Again, I believe it was economic and legal constraints. They're all artificial. They're not actually real reasons to make somebody be worried about it. Just the industry wasn't used to having it. And I think because of the openness and the ability to collaborate, starting with the Skywater and maybe some of the work that's been done here, where you get an open process technology and potentially fab, it will make it. Just because I don't think it's a technical challenge, I think, or technical shackles. And if it's not technical, I think there's a lot of talent around the world that will make it happen.
That's a very positive view. Has anyone got any kind of converse views to what Mohammed's been saying, or maybe finesse on it?
Not so well. I've got a similar view, I guess. So there's a lot of, if you look at pretty much any product that's reasonably complex, there's a lot of content that doesn't differentiate it.
Hmm.
That's one of the areas where I think there could be a place. You know, we heard about an open source Wi-Fi solution. If I'm building a product that needs Wi-Fi, but the Wi-Fi doesn't differentiate the product, it's just got to be there. At some level, you don't care which Wi-Fi it is. It just needs to work. It needs to be there. And once you've met those two criteria, you're done.
Yeah.
And you focus on what differentiated your product. I think there's a big place for trusted solutions. Once open hardware's got to the level of maturity where we know it works, in the same way that you know open source, you know, certain open source software packages, you know they work, you know you can trust it. Once it's reached that point, I think that there could be quite a big opportunity.
Yes, I think I'd agree totally there, David. Anyone else got any thoughts around this? Sally, you from the audience?
From the yeah. So from my perspective, kind of from the semiconductor industry, I think we are at a point now where we're seeing such a lot of renewed interest and such a lot of investment going into the world of hardware and to chip design, basically driven by these new applications, AI, 5G, and the kind of rise of domain-specific architectures is kind of coming together to make hardware cool again. And I feel like we're kind of at a turning point with it, where hardware is becoming cool again, and open source hardware can be a big part of it. Removing or reducing the barriers to entry for smaller companies, startups, SMEs, and even for makers now registering to make their own SoC designs or to even design their own cores. Reducing the cost of the license fees that you'd have to have from a bigger IP supplier or somewhere else. But the other thing that's very exciting is, of course, you also get the level of flexibility that comes with open source. You can build on the IP that you've got, or you can tweak it, which of course isn't there with what you get from other suppliers. If you want to buy a microarchitecture license from ARM, I mean, you've got to be Apple basically to be able to afford it. So I think we're definitely seeing increased levels of innovation for sure, driven by these new applications and taking advantage of open source hardware. So from my perspective, I mean, what I see is, RISC-V certainly is often, people often compare it to Linux, talking about the open source software world of the 90s there, people, RISC-V as the Linux kernel really starting it all off for everything else to grow from. And I think in this analogy, you've got companies like Sci-Fi and Andes then become analogous to Red Hat. But when it comes to, what do we need for this open source movement to really be a success? You've got to have, firstly, you need to build a community around it. You need to have people building cores, building the boards, building reference platforms and software. RISC-V and this community, I feel like they're really gathering momentum. They're doing really, really well. So that's very encouraging from the open source side. And if we want to make, if we want to have this ecosystem of companies actually making chips based on these kind of open source technologies, hardware, it's so much more complex than software. It's not like when you write some code and then you push a button and you can distribute it, publish it, ship software. I mean, maybe I'm oversimplifying
maybe
a little bit there.
we could get to that,
Yeah, maybe I'm oversimplifying.
Maybe somewhere down the line there's a future version of David's work where everyone has a little box in the back of the room.
just suddenly build
the whole thing.
Print out an ASIC, right? No, there are so many more layers to the technology stack for hardware, especially when you go to manufacturing. That's a whole technology stack on its own that, we're talking about decades to build this kind of technology stack for open source. So I don't know. there's a lot of different elements to it. So you need the EDA tools, you need the manufacturing technologies, all these things have to come together with the community as well. So you need all these puzzle pieces basically.
Yeah, I call it the AND gate, and probably some other people saw this. It's an AND gate that has the EDA, it has the PDK, it has affordable manufacturing, it has knowledge, it has IP, and it has a customer. That's a very important aspect of this. I just wanted to comment. I forgot, actually. I don't know why I didn't do that. I'm supposed to in the chat. The first shuttle that Google funded on 130 nanometer was Skywater, was overbooked. Okay, it was 40 chips. The spectrum from we have like more than about 5 RISC-V implementations, and we have an open power implementation. And when I say we, I mean the community at large. I'm not saying eFabless actually. And you'll see analog and digital, and this is impressive. So that's actually one of the anecdote data points that show just when you open the door, the flood happens. And one component is to simplify things to enable. One of the things that was actually very successful in the shuttle with the Skywater is we primarily driven from Tim Ensler from Google saying, I'm coming from the software world. I don't know what a DRC is, how to do a physical design. So basically treating the RTL to GDS as a GNU compiler. It needs to compile. I don't know how to build a compiler, but I know how to use the compiler to do a lot of things with it. The flip image of that, which is want more people to use used to be, there are many proprietary names that are around compiler, but I don't want to just say it is actually just the analogy is valid. And one thing you mentioned something about RISC-V. So Sci-Fi, RISC-V, and these, RISC-V, and then all the companies they're evolving that with a lot of architectures. One thing I keep saying to everybody: cores are not enough. Cores are not enough. You develop cores, you don't develop chips. Cores are the kernels or
libraries.
That's the thing. You need access to the real world, so we need communications. We need sensor interfaces. This is today, the vacuum is there, and I keep preaching that everywhere. We need to get more useful interfaces that are in the open, so people can use them and build useful chips applicable to real applications.
Analog is hard, though.
Absolutely. However, I'll tell you one thing: when you cast a wide net, like if you try to look around here, when you cast a wide net around the community, I found that they're amazing. Analog knowledge and capabilities, especially with automation. Yes. Yeah. So.
I fully agree with you. I was just dovetailing as to why I think there might have been a bit of vacuum there. Is that I think we've had a lot of focus on EDA and progress in automation, IP sharing on the digital side, like with the RISC-V and all that sort of stuff. But we don't talk about like a common band gap model or DAC, ADC, all these like just jelly bean elements that really bring a SOC together. Everything you need to build, like we have all the elements, but I think of all the pieces that are going to be really the sort of the thing that prevents that whole thing coming together, it's going to be things like the analog pieces, the eFuses, dense RAM cells that are actually fully open, these types of things. Those are a little tricky because they actually require a lot of process integration, a ton of runs, really good characterization, really good transistor models, and those are really boring things that, like, you want to fund someone to do a test chip full of nothing but transistors with 20 gigahertz FT characterization things and rent like a $200,000 scope to do it, put out the data, create the SPICE models. It's a very unthinkable task.
Well, yeah. You say that. I've seen in the open source world over my 20 years or odd years now of it. It's amazing what people like to do.
Yeah,
this is true. This is true.
Literally, Strive. We've had this chip Strive that we eFabless were doing the design, but we didn't have enough resources or time to actually test it all the way to every characterization direction. So we have volunteers. For example, Andrew Zonenberg he took it. We're sending the boards, parts, and he's doing the job on the other side. Okay.
And you make subthreshold characterization cool again.
Yes.
Yeah. Well, yeah. I've talked with people doing, trying to do time domain analog with subthreshold and the whole async logic people. They've been coming back again. Like, oh, hey, we can do this now. Which kind of Actually, I really wanted to ask Jana because, there's all the stuff you work on is some of this is going to be the future of where we go. In the non-silicon future. Can you see how this could, drive that, or the push and pull between those two?
Yeah. So yes. So from these keywords that you mentioned and also Sally mentioned, right? If you think about hardware for AI or 5G and so on, it's likely not the same technology that we will be using and just going to 2 nanometers or trying to shrink just in the normal standard formats, and the procedures will not be the way to go. So what we try at INL is to develop new type of technologies that could be new paradigms for computation, including neuromorphic spintronics approaches or neuromorphic nanophotonics approaches or quantum photonic computational approaches. And besides some theory groups that are working more on the theory behind this and also quantum software engineering groups, we have a lot of groups that actually work on hardware, right? And on chips that demonstrate new functionings that could be building blocks of energy efficient and solutions that can also track problems that are intractable with classical computation. And so in that sense, I think that some of the strategies mentioned today are foreseeing that the open source hardware platforms that could be used to integrate technology platforms are first robust, but also flexible. So you can learn them, but you can adapt them. And maybe for a proof of principle type of chip, you could actually, integrate that and play around with it to make a proof of principle device. In this case, I'm speaking with those groups that work on the very low TRL readiness, on the technology readiness level. Then, of course, at INL, we also have groups that work on higher TL level. And when I ask them about, what do you think about, more flexible, implementation, I don't know, do your own CMOS chip or so, then much more, because we are able to show that our technology is really higher TL level, also expect to be integratable with industry standards. It's actually not really searched for that level of flex. So the integration is more embraced then, or is faster also to find support in funding or in a fund solution, rather than a more exploratory approach that might be of higher risk, and the gain may be later on, right? So I think that's a very interesting topic. As a researcher myself, being an experimentalist, being on the exploratory side more, I'm embracing these opportunities that seem to emerge. But I also see that it would be, I think it was mentioned. So it's right now it's communities where very self-engaged, self-teaching, and it's basically a lot of hobbyists at the same time research institutes, and we saw members of very famous research institutes, right, that work on this. But it also seems that these are small projects, it's not big projects, right? So I think to really leverage that, there might be movement. It's bigger and growing, but still it's visible that they know all each other. So I think there's still room for growth.
Yeah, I was just thinking, could you imagine a future where, say, one of your experimental technologies, you invite community out onto to build things with the technologies and have a collaborative open
Yeah, I
source
think
model
so.
there.
I think certainly, I foresee that for many of these groups on the lower TRL level, that could be very interesting. Those with higher TRL level research, I don't think would be very open to that. But so, yeah.
Makes sense. Thank you. I was going to ask Maria, but we've lost her. I hope she's.
Just one moment, please.
I can hear you. We just can't see you. Okay.
Yes. Sorry, one moment. Just. I think I'm back.
There you go.
Okay. Sorry, I had to move because I was running out of battery on my laptop.
Very good. I'm glad you managed to find some power.
Yeah, no, just to quickly wrap up, I basically, I agree with all the ideas that have been discussed, and mostly, especially from the business point of view, I think was David who was mentioning it. It's a matter of trust from the customer's point of view. So if we are going to build an ecosystem or an open source product that customers will buy one day, and we are going to build a business from this, we need to be able to create something that is reliable and that interests people and meets their demands. So yeah, I mean, there are many hurdles on the way that we have been commenting many of them, and just from open source PDKs that we don't have, especially from big founders, right? If you think about going to high volume productions, now you need to go to the 3 big names, and they are not in favor of open source technologies, right? So yeah, this is something big that we have to overcome. And then EDA tools also is something, especially post-verification ones, that we need to improve them. But I have seen today that there are many projects that are really working on this. And yeah, working in large node technologies is something that can really help in there to innovate and also to improve. So yeah, I think this is really encouraging. And well, I see a lot of room for improvement. So yeah.
Thank you. Yeah, so we kind of takes us on to the last question, which I think we've already started touching on already, which is the roles that we can see open source and projects like we've seen today playing out for the EU specifically. And we know we're looking at the EU industry and academia, I think, especially, the economic side of semiconductors in the EU. I think we'll also touch a bit on maybe sovereignty, which I know is a very common discussion point, especially around silicon at the moment. Do we think, for example, open source is going to help us with our silicon sovereignty in the EU? Is that important?
Well, I see the way we have it now is we have a system that is set up for very high volume and very low small process nodes, and that's where all the innovation has been going on lately. And now we are currently facing a chip shortage, and this model just doesn't scale. It's like we would say that, no, we can't make more software because IBM has too much to do. They can't make software for us. We currently have a system where only a few players can actually make these things. But I'm pretty sure that most of the people who want chips don't actually need to have these Apple M1 5nm things. They need something. And they might have a sensor that they want to put on a chip, and they need some SPI controller or CPU to go along with that. And I would be perfectly fine with a lower volume, higher node. But there are a lot of hindrances there, because now suddenly the cost of the EDA tools come into play. That becomes a factor, which is not as much a factor when you have a very high volume. So I think what we need to see is more foundries. They don't need to be top of the line, but they need to be there, and they need to be spread out. And we need standards. We have seen that over and over again, that we need standards so that you can take your designs and move it between these foundries.
Yeah, so and just a comment on this, even though I'm not from the EU, however, I'm not, I'm a citizen of the planet. So the number one, I'm just building on Olaf's comment. So there's what I call the right size compute. okay, which is basically find out what the application is, and you can go as aggressive as you can even go characterize the library for a certain application. So this is stuff that we're used to today from Foundries. You give you a library that's characterized for certain voltages, for certain specific conditions, but you can go do whatever. You can actually go customize beyond beyond what's available. The other thing in the industry in semiconductors, this is a fact. It's not publicized in general, like it's not socialized like this. The companies that build standard products, I'm not talking about the M1 standard products chips. I don't know, the companies that build chips in general, NXP, TI, NADI, all. 50% of the defined products. This is conservative. I'm not going to say the real number now, but 50% of the defined products and available in standard market on their marketplaces, they don't sell. Okay, that means they define a product or a chip and then put it in the market and it doesn't sell. It doesn't even bring $50,000 total, which it doesn't even cover the development cost. So that means that there's a huge miss in identifying the product, what is useful. And that means that large companies with large capital can only afford it because you have 50% kinda miss. So you have to, to have enough money to lose that and still succeed and be number one or number two player. Third thing is that actually chips manufacturing is a 3D printing process. Okay, so it needs to evolve to become like 3D printers, where this is your answer for the ubiquity and mini manufacturer, so it's still not there, but something like e-beam lithography and what is it, and then getting in that direction. It is a 3D printing process on a nano level, micro level, and if you think about it this way, you're going to get there. So standards are obviously important because I started the company. When I started, I would call it the fragmentation disease, is that there were no coherence in terms of efforts to drive the development together. It was everybody's doing single things, like a tool here, an engine here, but they were always working alone. And so having standards enable us to really lubricate that process of collaboration, actually building on top of what other people do.
Well, I can't agree more. I mean, the 10 years I have been in the open source silicon world, the focus has been on collaboration more than anything else, because there is so many good things out there, but the lack of collaboration has meant that no one knows that they are there. They can't be used together. And I mean, a project like OpenLane is a perfect example of someone taking the effort to actually put together all the pieces that have been out there, filling in the gaps and making an end-to-end solution. I think it's great.
Yeah, just you mentioned OpenLane, I have to mention OpenRoad because the OpenRoad is actually a great team. It's actually a project that was a fruit of a U.S. government DARPA project that was funded specifically to build open source, no human in the loop compiler from RTL to GDS, and actually on the board level as well. So we work closely with the OpenRoad team, and you'll see us even working closer. But it's an open source project all the way. But also the good news is the team that's working on OpenRoad, when they started working on advanced technologies like 12 nanometer. Okay, and they have done tape outs on that. The only thing is the process is not open source, but there are chips that are being developed by open source tools in 12 nanometer, but they are enclosed containers.
Yeah, and I mean that's a really valid point in this conversation. Why are the US? Maybe we could talk to why the US are funding that. What's the driver for them? I know, Mohammed, you've had some exposure on that, and I think that's relevant to this EU discussion.
Well, so if let's follow the breadcrumbs. So for a project like this is started by Andreas Olsson, who, if you look at his history personally, he's created a Parallella project, or and he has a history of doing things and showing that he can actually, even with with proprietary tools, he was able to get with $1 million alone to build a compute platform that is 64 core, I think, and he funded it on Kickstarter. And he said, hey, I can do it. So he solved the knowledge aspect because I know how to do it, but he used the money to get access to the tools and the process, right? So he solved that piece. Now, if you look at it, he became a part of the DARPA, and he drove that program. I can't speak for the details. I don't know what magic stick or what carrot that he used to justify the tens of millions to get from DARPA. Now, what I'm aware of now, based on the Google project, when we presented the results of the effort and showed that you can multiply the number of people making chips, designing chips, by making it straightforward and simple and collaborative, and also by the number of designs that showed up, just 45. That's the ones that showed up on the first one. If you imagine that in a couple of years and you have thousands of designs, now that was appealing in terms of an ecosystem development for someone like the government to say, okay, well, I can use that as a potential reservoir of trusted designs. When I say trusted here, trusted by transparency, and of course, they have to be verified. So there is a movement there that is call it self-motivated, because you don't go do open source just from from their perspective, just to open up everything. Is basically to benefit from the process of collaborative and collaborative verification and development of a lot of designs. Okay, and then you'll be able to tap into that and build other things that are potentially, you can hide them, but you can use a lot of the open source code. This is the view of the government. The second part, which is
so guys, so just to recap there. So you're saying that the government is funding this work in the US in order to generate more homegrown silicon competence. Is that what you're saying?
This is very important. Yeah, that's my last point was that, and I know just at a time, is the education. There's you can read online. There is a huge depletion of interest in engineers or to go into that field, and there is a movement now to do two things: stimulate it in a way that it makes it actually, why would I go there, and also make it actually get it more in the undergraduate education. And our solution for that proposal is really based on the open source design.
Yeah, I mean, I'd love to see us providing education at the school level, right? There's no reason we can make.
My LinkedIn profile, I have it on there. 14-year-old.
Yeah, I think that's a future I would like to see, where we have programs targeting the inner city schools, helping kids learn how to digital design and build their own chips, right? That's a future I think we can get to quite quickly with
and then fabricate it in your garage.
Exactly. or well, at the moment I think we don't need to do that, but yeah, eventually if people are buying the little rep machines, one for the school, little ASIC, maybe it's a 1 micrometer.
I still think, and I mentioned it before, a CD drive or a DVD drive has a laser pointer that is actually less than a micron, so you can build not 130 nanometer, but you can build upon that and to use it for lithography.
Yeah. Is security an angle here? Does anyone want to talk about security and open source?
Money.
Yeah, I mean, from the standpoint of, just trust and security. There's always the question of do I actually know what's inside of this chip, and that it trickles all the way down from the fact that you're just getting a black piece of epoxy and someone says trust the top mark, the inside matches what's on the inside. To okay, fine, we know that the chip, and we've tracked the custody chain all the way, even to I've heard a lot about EU being like, well, we have to have trusted domestic fabs or whatever it is. I mean, is the design itself completely intact? Has it been verified? Are there backdoors? These types of things. And so there's definitely, if you have any interest in the security side of things, the transparency that you gain from an open source process, obviously, a lot of eyes looking at it is going to be important. But to facilitate that, there needs to be more sort of cross abstraction layer collaborations. Like the people who do formal verification know nothing about GDS layout. The guys who build computer board systems know very actually little about what goes inside the silicon. And really where things tend to fall apart is in those intermediate layers. Too much focus on one single aspect of the problem, like we're just going to build a trusted fab and that's going to solve all our problems or something like that. We'll give you chips that may have been created in a foundry that you trust, but then the actual place that puts the chips in the board is not trusted. You've wasted $10 billion, when someone can just walk in with a FedEx package, swap out some stuff, and then put chips that came from some other fab, on the board, right? It really needs to be, from the security angle, has to be, sort of a full stack solution. And I think also just to maybe dovetail onto that, one of the things that as we start approaching a more open, more adoption of sort of openness and open technologies in the public, and we're going to have to train people on this, is that hardware has bugs. Okay, like even if you think that your hardware doesn't have bugs, it has bugs, right? There are erratums sheets that are like 1,000.
No way.
Yeah, oh my God! Like, there's a bug in my hardware, or people design whole blocks into chips and never get turned on. These types of things.
Yeah.
If you
as someone who's hit many of those hot hardware bugs in my career, I could
yeah. And so actually, it's going to be a really hard fence to jump over, because a large company will be able to say our hardware is perfect, we have no bugs. And people will believe them because, for 20 years, Apple shipped a CPU without a bug or whatever they claim it is, right? And then the first open hardware CPU that comes out that claims trustability and all this sort of stuff, well, we're going to have a list of bugs. We're going to know what the bugs are. We're going to tell you what they are. I mean, if you're doing it right, you're not going to have an NDA to know what those bugs are, right? And that's actually a better situation to be in. But from the very outside, it's going to seem like a huge waste of money to the public. It's going to be very difficult for people to accept hardware that superficially seems more buggy or less good. So there needs to be some education program, some marketing that has to go around this that really builds the market around these types of things. And that is going to be from the trust and security angle. It's not that we're going to build it necessarily better than they can. Is that we're going to know what the bugs are. We're going to tell you what they are, and then you can patch them on other levels, and we can work with people across levels to patch these holes. That's where we're going to win. We're not going to actually necessarily build a stronger wall or a better castle than a very well-funded company can.
Well, I mean, that goes to one of the dirty little secrets of the whole industry, doesn't it? That most products only just work, and most companies, if they're honest, actually have no clue how most of their products work.
That's right. It's true. No, I've used it. It's crazy.
As somebody who's filed silicon errata,
and even the use cases. So that's the use cases. So you only verify for what you know. That's one. Yeah. And the open aspect of this, it creates parallelism and diversity of stress. So you can bounty something, put a bounty on something to break the shit out of it. Can do a lot of things like that. So.
We're gonna look so much worse on our first chips out, because we're gonna have such a thick pile of erratum compared to whatever else is in the industry. But we're actually better. It's just we have more because we know where bugs are, right? That's where we're gonna start.
The key is actually iterative, low cost. So this is when you do it instead of just try to perfect it, like iterative, low cost, getting out and modify and
sure, yeah.
And the last example that I saw about this. And whether you like SpaceX or not, but they build rockets very quickly. It turned out that the fundamental principle there: don't perfect the rocket because it's unmanned, especially the Starship stuff. Build it, make mistakes quickly. They don't even have a production line.
Right.
And you break all the explosions and all that stuff. They were expected, in a sense, there's a probability, but that's their process in terms of build it quickly, and then when you reach a level of maturity based on the iteration of lower cost relatively, you mature.
No, you're completely right. But the one thing that's different is that SpaceX is their own customer. So when they blow up a rocket, it's from their own money. You try to explain to Volkswagen why your engine control unit has a bug in it and they've shipped it in 1 million cars. And it's not a big bug, but it's a public bug, right? And then who is going, who are they going to come after? Whose blood are going to squeeze from a stone, right? And then they'll be like, oh no, we should go with NXP for sure. NXP, like, we don't have any bugs at all. We'll stick with those guys. This open source stuff is crap because they have these, look at the list of bugs. It's going to be so hard to argue against it. I mean, I'm not, I don't want to be a naysayer, but this is
in the beginning.
This keeps me up at night, right?
Agreed. I do think it's in the beginning. I think because people like you and public and educating and informing other people about this and the importance of this, I think it's going to be resolved over time.
Yeah, but we're going to need to have a lot of good messaging. We're going to have to be, as a community, ready to say the right things. We're going to have to be able to, not internally fight. If we had two competing solutions and one part of the community is fighting another part, BSD versus Linux kind of war, these types of holy wars, Emacs versus VI, that's not going to be of a benefit when you have
and that's what I mentioned
real
by
dollar.
That's what I was the disease of fragmentation. That's exactly what I mentioned here. Is that that it was on the EDA side though is different tools, different things are being done. And then people are attached to the measuring the success based on one thing rather than the collective. Let's go together and do something bigger.
Right.
But to your point about bugs, I mean, that problem exists today. If I go license some piece of IP, the vendor says it's perfect. There's nothing wrong with it. You put that in your chip. And then you go back a year later and they tell you there's another revision. It's like, well, why is there another revision? It was perfect. That question about bugs, it's there now, just not visible.
And actually, they don't guarantee stuff that's going to automotive. They don't tell you it's perfect. They tell you, well, we're going to back you up with liability, or they indemnify themselves.
Yeah, and you have a process. You have ISO 26262, right, or something like that, and it's the process that means that they're covered and people can claim their insurance.
then that's the answer. An open process as well in terms of that and using.
It's just having someone who will provide the indemnity and the insurance and the support, right? Much like Red Hat did in the early days of people using Linux in banks, right? It was a big thing. We're kind of nearing the end, so I just want to. We haven't quite heard from Maria, Jana, and Sally. So I'd like to just throw. What do you think this is going to mean for the EU in the coming period? Maria, go on. I'll put you on the spot.
Well, do you mean the projects that we have seen today, or
the open source in general?
Open source in general.
Coming to this space, yeah.
Well, I think it's a really good opportunity for the European Union to be on the spot of innovation, as we have said already. So, because all these projects, they are kind of tackling the problem from different sides, meaning developing standards, we have mentioned it. We mentioned about EDA tools, PDKs, legal and regulatory frameworks. This is also very important, and we've been talking now about security and the trusting issues. So I think there is an opportunity for the European Union, and we should go into this train, or if not, we are going to miss it for sure.
Thank you. Jana?
Yes, thank you. Well, as I mentioned, so I think it would open a lot of flexibility, which connects to this potential of, kickstarting innovation and exploring new ideas, right? So I think that Europe, because thinking of these investment packages that are made now in silicon and trying to create Europe like a fab house for standard silicon chips, I don't think this would make Europe like competitive compared to Asia or the where this is where they have the production power right now, right? So if there is to differentiate, this is probably with the new type of hybrid or new type of technologies and platforms. And so if open source hardware indeed can be more flexible to be integrated with hybrid technologies, that could be very, very interesting. Concerning the discussion about trust and society, we know, of course, that the Eurasian Europe program is certainly putting a focus on that. So any technology and proposal should also connect to trust and society. So I believe that that is another topic that was very clear from the projects shown today, right? That the type of bugs that is mentioned also here in the comment section, the maker that knows about doesn't care about their own bug as long as he understands where this comes from, right? If you have the control over that issues and you may be able to solve it in just the next iteration, it's not such a security threat that could be any other bug that is in a platform that I don't know about. So I think these two aspects make this for Europe a quite important movement from my impression, from the researcher perspective and from coming from the research innovation ecosystem. I believe that is certainly interesting to connect this open source movement with the academic research innovation scheme, and I hope that actually these funding mechanisms are supporting projects that are covering these this ecosystem, like connecting us. So first of all, or last, now like closing, right? Thank you for inviting me in this community, which is new to me, and maybe this is part of creating such links across these
absolutely. Thank you for joining the board. I think I was really eager that we get a really good cross section across academia and industry and EU and a bit of the US and current people delivering today and people thinking about what open source is going to deliver tomorrow. Sally, have you got any thoughts around this area?
Yeah, so I agree with Maria, what Maria was saying. I think that, open source hardware is a big opportunity for the EU in terms of encouraging innovation and trying to build this ecosystem of companies and enabling this ecosystem to flourish. In terms of sovereignty, which is something that we've been touching on, obviously we're in the middle of a US-China kind of trade war at the moment, and who knows what the fallout from that was going to be. But for the EU or for EU companies, I agree with what Ulf was saying. Ulf raised this earlier. Most people are not looking to make the Apple M1. We don't need 5 nanometer or 2 nanometer processes. Maybe we need to build more foundries, but it doesn't have to be quite the state of the art. It needs to be something that works for us, that suits the customers that we have here in the EU. So, I think open source can be a huge part of it.
Thank you, Sally. A really good summary there. Well, I think if not, has anyone got any last minute things they'd like to say?
I'd like to say something. I put it on the chat. There are 3 Google-funded open source manufacturing runs this year. Mid-June, mid-September, mid-December. Go and use it. Start it. It's actually, there are 50% of the people on the previous 40 chips, 20 of them did not do a chip before, did not design it, and they actually spend the effort and were able to get it to verify it successfully on the front end side.
It's kind of, what we really need is something where it's running in the EU, right? So everyone wants to join. I've been trying to reach out to the right people around this. So let's keep. If anyone wants to join in with that, that's great. Let's.
And we have a follow-up on some European activities, yes. So, but I do want, in the absence of that, here's the thing.
Absolutely, let's get started.
The success of this propels the success of the movement, and it shows an example. Okay, So I although it's not coming directly from the EU, however, it's open source. So everything that gets there, the outcome is open source. So it's useful to the whole world, irrespective of who's funding it and where it's
going. That's a really important point. And Michel makes a very good point in the chat that the NLnet, is it the Zero fund this time, Michel?
It's we have a number of funds, so but do submit and we'll try and figure out how to fund it.
Brilliant. That's the sort of thing I like to hear. Cool. Thank you very much to everyone on the panel. It's been this is a bit this is as good as a conversation I thought it was going to be. So thank you all for you showing up and really bringing your brains with you, because this has been certainly a really interesting, and I think hopefully some point in the future we'll look back at this conversation and go, that was really important we had that conversation.
Well, thank you
thank you very much, everyone.
I enjoyed it.
Thank you.
Yeah.
Thank you.
Well, for the sake of posterity, as I mentioned, if this is going to be one of those important, cannot be missed talks, fortunately, all of this is being recorded. I will also do my best to share the public chat for any links and mutual introductions that were made. And as well, if there are still people from the NGI Zero projects, thank you very much for presenting. Would you also be so kind as to share your slides with me? I saw some people already asking that as they were interested in your work. We will also make these slides available all on the NLnet website, where you can find a link with all the information about this workshop. Thanks again to everyone joining in for the lively discussion, for the presentation, which were very insightful, and for all the different perspectives, which were very concrete and future thinking, which is always nice. And I agree that this should continue somewhere. But for now, thank you, everyone. Have a good evening. In a few minutes, I will close. We'll stop recording of this room, but leave it open for anyone to exchange contact information. Thank you, and good evening.